Alright, so in our last video we looked at vectors in 2 dimensions and how to add vectors and break them apart. And now we'll see why we would do that. Breaking vectors apart into components, like we did in that last video, can be very useful when you go to work problems in 2 dimensions. You can reduce a 2-dimensional problem into 2 one-dimensional problems. So let's start talking a little more about projectile motion. And let's imagine chucking something into the air. And so what I've got here is a motion diagram. Each of these dots represents the position of some object as it would be flying through the air. So if we were taking snapshots with equal separation in time, equal time intervals, the ball would start here. It's moving upwards pretty fast. It's also moving sideways. It gets to here. It then moves upwards, but it's slowing down, still moving to the side. It reaches its peak, no longer moving upwards. It begins to move downwards, still moving to the side. Moves downwards even faster, still moving to the side. And at this point, it's moving down quite fast and still chugging away sideways. Now, I've labeled a grid over top of this motion diagram, so we can look at the spacing between each position. Now, if you recall from Chapter 2, we can infer some information from that spacing. And when we take a close look, we can see that in the x direction, or the horizontal direction, we can see equal spacing. This object moves the same amount of distance in every time stamp in that x direction. Meanwhile, we see increasing or decreasing spacing on the y direction. We've got a lot of space that we cover here. We cover a lot of distance in that first timestamp, but then less, and then less. Then we start going the opposite direction, and then we cover a little more going down, and then even more. We see increasing spacing in the y direction, equal spacing in the x direction. And if you recall, what those show us are constant velocity for the x direction and constant acceleration in the y direction. We can look at the spacing of our motion diagram and infer that whenever something is thrown in the air, when it becomes a projectile, its x motion is given by constant velocity, its y motion is characterized by constant acceleration. And if we think about the two equations for position, we can see that the x position, or displacement, simply depends on time, depends on t. dx equals vxt. That would be our position equation for constant velocity. If we look at y, the y depends on t squared. Our y displacement is given by v naught yt plus 1/2 g t squared. And when you have one variable dependent on t and one on t squared, that gives you a parabola. So the shape of the trajectory, the path an object takes flying through the sky, is a parabola. Everything that is thrown up into the air forms a parabola. Now, that is imagining that there's no wind resistance, a lot of other factors are taken out. Really, things fly up and then wind slows them down and then they kind of drop almost in a straight line. But we're not going to go into that much detail. This is still, Physics 1, Physics 1030, Survey of Physics. We're just getting an introduction to physics. And based on our motion equations for constant velocity and constant acceleration, this is the shape a trajectory should have, a parabolic arc. All right. Well, we already know what the equation should look like because we already are familiar with the equations for constant velocity and constant acceleration. Nonetheless, I will write them out again for you with some subtle differences. So, let's look at our x equations. In the x direction, we have constant velocity. So our x displacement is simply given by velocity times time. That velocity never changes, and so whatever it is, we cover so much ground as time goes on, and how much time has elapsed will determine how our position has changed. And really, these other equations are just this same equation solved for the other two variables. So we could also solve for the x velocity as what the displacement is, how the x position changed over time, or we could find the time as the change in position over the velocity. And because this is constant velocity, our x velocity is equal to the initial x velocity. It stays the same. It's constant. And this is important because it's not true for the y direction. Y direction is undergoing constant acceleration. So no matter what your initial y velocity is, after some amount of time, gravity will have changed it. So we can have some different velocities in the y direction. We can have an initial velocity, but after time has elapsed, it's going to change into some final velocity. And that's how that equation is read. We start at some velocity, gravity changes it over some amount of time, and that leaves us with some final velocity. We also have our displacement formula for y. The displacement in the y direction depends on the initial y velocity times time plus 1/2. Normally we have at squared here, and I actually put this into the previous equation as well. But instead of acceleration, we can go ahead and put in the acceleration of gravity. We know that the y acceleration is going to be that of gravity, and it's always going to be that of gravity. So I've gone ahead and just put it into all of these equations. We don't need to think about what's the y acceleration. It's always gravity. This is something you can always write down as a known quantity whenever you go to solve projectile motion problems. Just like in Chapter 2, I'm not going to say, remember, gravity accelerates things at negative 9.8 meters per second squared. That is just a fact sort of lurking in the background that you should know. And of course, we have our third equation, the special one that doesn't involve time. The final velocity in the y direction squared would be equal to the initial velocity in the y direction squared plus 2 times the acceleration, that of gravity, times the displacement in the y direction. Now you probably noticed that I put subscripts on everything to keep these separate. Over here we have displacement for x, velocity for x. Over here we have displacement for y, velocity for y. But you may have noticed there was one variable that I didn't put any subscripts on. What is shared by both x and y directions? Time. As time ticks away, the same clock is ticking for x as for y. So time is sort of what ties these two directions together. They share the same time. If 2 seconds has elapsed for x, 2 seconds has elapsed for y. This connection is usually the key to projectile motion equations. We're often going to use one direction to solve for the time, and then once we have that time information, we'll take it to the other direction and get whatever information we actually need to know. And you'll see this again and again as we work our examples, which we'll get to probably in our next class period. But time is the key, and I want you guys to keep that in mind. You might find time with x and take it to y. You might find time with the y direction and then take it over to the x direction to get your final answer. But either way, that is usually the process through which we go, that we go through in projectile motion equations. I do have some bonus equations. You do not need to know these, but I figured I would show them to you for those of you who are curious. You can take these equations and you can combine them and predict things like the range a projectile might travel. This is in the x direction. How far in the x direction will it travel before landing back at the height it was fired? And that is determined by the velocity squared. This is the full velocity, whatever direction it's pointed in. The direction information is here. The angle above the horizon. Really, it's the sine of 2 times that angle, and then over the acceleration of gravity. How high, or the maximum height that your projectile will reach, is given by this equation. Initial velocity squared times the sine squared of theta over 2 times g, the acceleration of gravity. These can be used to predict where your missile is going to fly. Of course, it gets much more complicated in the real world. As I said, there's air resistance we're not accounting for. If you launch a missile up high enough, you actually have to take into account how the world turns underneath it. For instance, if you throw something straight up, if you throw it up high enough, by the time it falls back down, the world may have turned. That's something called the Coriolis effect. A pretty cool thing to look into if you're curious. But anyway, that's the basics of projectile motion. You have 2 different directions. We will work them separately, breaking 2-dimensional problems into 2 one-dimensional problems. All right, so that's the end of this video. We'll come back next time and look at circular motion, another type of motion in 2 dimensions.